So the last part of this lesson is talking about the electrolysis of water. Okay, and the electrolysis of water is taking water, okay, and splitting it up into its atoms. In this case, we're going to form hydrogen gas and oxygen gas. And remember, you need these twos here, because they're diatomics. And if you look at sort of what happened, so hydrogen is +1, and hydrogen is 0 here. So if the oxidation state went down, so hydrogen was reduced, and this one went from -2, or oxygen went from -2 to 0. So oxygen was oxidized. Okay. So what we're going to try to do here is calculate how much voltage it takes to do this. Okay, remember, this is an electrolytic cell, so we need to do it. We need to use a battery to break down water. So if we go to our tables that are here, I'm going to look for the half reactions that contain water in them. Okay, so if I take a look, we have this half reaction, which contains water, and it won't let me write, so we have this half reaction here that contains water, and then we also have at the bottom this half reaction that contains water. So I'm going to go back to the smartboard, and you'll see on the next slide, okay, I have put those half reactions there. Okay, and our goal again, remember, is to calculate the voltage, okay, that's required to do this. All right. Well, if we take a look at these things, we said, okay, well, this went from +1 to 0, so it was reduced, and we see for hydrogen, the one with hydrogen, this is written in the reduction form because we see the electrons are being gained. Okay, but we said that oxygen was oxidized, so it went from -2 to 0. So this reaction here, this is a reduction reaction because it came from the reduction table. We need to flip it. All right, so I'm going to rewrite it flipped. So we're going to have 2H2O, and then on this side produces oxygen gas plus 4 hydrogens plus 4 electrons. Okay. Now, because I flipped that reaction, okay, I need to change the sign, so I need to make this sign negative. Okay, so now just to show you that this works, I'm going to add these two half reactions. Remember, to add the half reactions, I got to balance the electrons. So I got to multiply this side by 2. So this becomes 4, this becomes 4, this becomes 2, and this becomes 4. And what we see when we do that, okay, sorry for the pause, someone entered the room to ask me a question. Okay, so we need to add these two reactions. So if we add them, okay, and I'm going to change the font here. So on this side we have 6H2O. We have to add those two together. And then, so the electrons cancel. And then on this side, if we add those together, we have 2H2O and oxygen. Okay, now we have this weird 4H4, like that, it's weird, and they can't cancel each other. They can't cancel each other out. But what is this actually? So you have an H and an OH, okay? They're actually going to combine to make 4 waters. Okay, now there's 6 waters on the product side, sorry, on the reactant side, and 4 waters on the product side. So these are going to cancel out, and you're going to be left with 2H2O, 2 hydrogen molecules, and then O2, which is the reaction that we started with. Okay, so now the whole point of this, okay, was to find how much voltage it would take. And remember why we flipped this sign is that we had to flip this reaction because oxygen is being oxidized. And all we have to do is add them, right? So if we add those two numbers, which I cannot do in my head, we get 206. And remember, it's negative. So what that means is that doing this reaction, you would need to supply 2.06 volts in order to do it. Okay. Now, if we look at, this is an apparatus that's set up to do, it's called the Hoffman electrolysis apparatus, set up for the electrolysis of water. And there's something wrong with this picture. Okay. If you notice, okay, so here, these amounts are equal. And the question is, should they be equal? So like here, this is water, right? And on this side, if we look, so here if we look, sorry, again, interruptions. This is where, so we look at the battery, this is the negative end of the battery, so the electrons are coming in here, Okay, and remember who's being reduced by these electrons? Well, hydrogen gas is being reduced. And then that pulls the electrons, right, from here. So on this side is the oxygen gas being produced. Now, if you notice, these levels are equal. And that shouldn't be the case. Okay. Now, the reason why that shouldn't be the case, if we look at the balanced reaction, okay, there's a 2 in front of the hydrogen. Okay. And there's only a 1 in front of the oxygen. So, in actuality, when you break down water, okay, this is the gas up here. The gas is being stored up here. Okay, this water level should be lower because you should generate twice the amount of hydrogen gas. Okay, so now, if we look at a more simplistic form of this diagram, so here we have our battery, and here we have, once our negative N, generating the electrons, right? And then here, the water, the hydrogen in the water is accepting those electrons and becoming hydrogen gas. Okay, and again, this is the reduction, right? So this here is the cathode, right? Now, because electrons are being drawn, okay, they pull the electrons out of the oxygen. And here, the oxygen in water is being oxidized and collects up here. And then because we're having an oxidation, this is the anode. Okay, now, and we can see the half reactions here. This is the hydrogen half reaction. This is the production of oxygen half reaction. And again, once we can see in the correct picture, the amount of hydrogen is larger because of the 2 in the equation when you balance the overall thing. So that's the overall picture here. So what do you really need to know? So when you electrolyze water, you need to know what's happening at the cathode, okay, which is the reduction of hydrogen in water, and what's happening at the anode, which is the oxidation of oxygen in water to create oxygen gas. All right, so there's one last thing, which is a little math related, and then we'll be done. So this is combining the lesson that we did in class with the lesson that we just did about water. So this is saying that we have a solution of potassium iodide. So what that means is you have potassium iodide dissolved in water, okay, and you're going to pass electricity through it, okay? And the question, okay, is, okay, so what reactions are going to occur? Is the Ki going to break up and form potassium solid and iodine, or are we going to break up the water? So our two possibilities for our reactions, okay, is we have Ki, okay, and we could form K solid plus an iodine. And again, we need to balance this. Or the other option, again, is that we could break water into hydrogen gas and oxygen gas, and then we need to balance this. So the question is, okay, which one of those reactions is going to occur? So then what you have to do, okay, which I did on the next slide, you'll see, is break these into their half reactions. And again, figure which ones are the least negative. And the one that's the least negative oxidation is going to occur. And the one that is the least negative reduction is going to occur. So if we look at these half reactions, okay, this is the half reaction from the electrolysis of water that we found on our chart. And this is the one where hydrogen is being reduced. So this is a reduction. This is being reduced. And then here we have, this is from the potassium, right? Potassium is going to go from +1 to 0 when you're breaking potassium iodide apart. And this is also a reduction. So it's reduced. And then here we have the half reaction with oxygen when we're decomposing water. We're performing electrolysis of water. And here our electrons are here. So this is an oxidation. And remember, oxygen is going from -2 to 0. And then here, this is from the potassium iodide, or breaking potassium iodide apart. Okay, so this is going from -1 to 0. And there are our electrons, so this is also an oxidation. Okay, so remember, our goal is to figure out which of these reactions, because we have a solution that's composed of potassium iodide, and that's dissolved in water. And if we apply electricity, which reactions are going to happen? So again, what you need to do is go to that table and look up the standard potentials, so the standard reduction potentials. Okay, and I did that already. So, I mean, you should go and make sure you can find these on the table, but I looked those up, and here they are. So, again, when I look these up on the table, just remember that I had to flip the signs on these because these are oxidations, and you only get reduction potentials from that table. So if we look at the reduction half reactions, okay, here, this is the reduction half reaction from water, or the breaking down of water, and this is the reduction half reaction when you're breaking down potassium iodide. This one is the least negative. Okay, so at the cathode, that one's going to occur. Okay? And for the anode, okay, the one that is the least negative is the one that has iodine in it. So that one is going to occur. So what that means, okay, is you have a solution, okay, of potassium iodide, and again, that's potassium iodide dissolved in water. At the cathode, you're going to generate hydrogen gas, okay? And at the anode, you're going to generate iodine, okay? Not oxygen gas, because this reaction is too expensive to occur. We would rather do the one that doesn't require as much energy. Okay, so the homework asks you to do like a different solution, okay? They ask you to do like I think it's like lithium chloride or something solution, okay? So you have to do the same thing, is break the reactions down into their half reactions, okay? And figure out which reactions are the cheapest or require the least amount of energy, and those are the ones that occur. Okay, have a good long weekend, or it's probably Monday, so you already had a good long weekend. I'll see you tomorrow.